As I said, our last talk of the day, we have Michal, and he's going to talk about Xref.rs. So a little bit more Elixir, Erlang, and Rust love going on. And I'll send it back to him and see you guys a little bit later for some questions. Don't forget to ask them on the Q&A.
Surprise, surprise. Make yourselves at home at my apartment. And yeah, let's talk a little bit about Erlang, about Rust, and about Beam, and how we can use all of them together. So I'm pretty sure if you did any Elixir or Erlang, at some point you encountered the dreaded undef error, right? Telling you that the function you tried to call does not exist. And probably if you're ever deployed in production, especially using releases, you've also saw this error about code that actually does exist, but was not deployed properly together. So today I would like to tell you a little bit about how we can try to solve this issue and inform users about this issue a bit earlier than only by things crashing in production. My name's Michal Muskala, and I work as a compilers and tooling engineer. And you can find me on the internet in many different places. And yeah, let's explore where the problem comes from. And in particular, it comes from the way that Erlang handles code. In particular, the feature of Erlang code, which is the extreme late binding. And what does this mean? In particular, if we look at various programming languages, we can see two different kinds of languages or two different approaches to compiling the code into the actual executable. And binding here refers specifically to the way that the compiler and the runtime system resolve the name of the function to the actual code that's going to be executed, right? And so one of those approaches is early binding, also called static binding. And this means that the compiler will look for, if you call a function foo, the compiler will look at compile time for function foo, and basically rather than saying, in the compiled code, rather than saying, please call the function foo, it will say, please call the function at the offset 0x7, right? Which encodes kind of in native code the byte offset where the function could be found. And in some languages that offer both early and late binding, like C++ and Java, this is based on method overloading and basically uses normal functions for the dispatching. On the other hand, late binding, which is also called dynamic binding, means that this resolution takes place at runtime. So if the compiler compiles the code, rather than resolving the name of the function there and then during compilation, it will encode into the compiled code something like, please call a function called foo. And so only then at runtime, when you're actually executing this function, you will encounter this instruction saying call the function foo. The runtime system will have to look up what does the function foo mean, and only then you're able to call it. So as you can see, this way of doing things potentially has much more overhead, since every time you call a function, you have to go through all of this resolving. In many languages that offer both kinds of bindings, this is encoded using overriding or virtual functions and methods. And as I said, the address is computing at runtime. So far, this late binding seems like a fairly bad idea, right? It's just more expensive. So why would we want to do it? Well, because it gives us several very nice properties. In particular, it allows us to compile a module at a time. Right? So if we have early bindings, this means we have to resolve all the function calls while we're compiling the module. And if any of the functions changes, we need to recompile all the code that uses those functions. Whereas where we have late bindings, like in Erlang, we can compile all the modules completely separately from each other, with no dependencies and no understanding of what other code exists or will exist at runtime. And if any of the modules we call changes, we don't need to do anything, right? We just use start with a new version of the code, and it works. And this is extremely useful in case of Erlang for hot loading, right? Because what this means is that you can compile the module locally. You can then, without having any of the other code that exists in the project, you can later load it on the node and start executing and calling other functions that exist on the node, as long as you know they exist, right? Unfortunately, this also means that the check if a function exists only happens at runtime, right? And not only at runtime, but at runtime only if the function is actually called. And so, while very useful for hot loading, this becomes problematic for more traditional workflows, where like you have an entire code base, you compile the entire code base, and you deploy the entire code base, and you want things to just work, right? But then at some point you get the undef error and things start crashing around. So what is the solution? And fortunately, OTP comes with a solution for this problem. And this solution is the application called Xref. And this is a way more generic solution than just for this problem. In particular, Xref is this generic tool for analyze that allows you to analyze dependencies between functions, modules, applications, releases in a very abstract way. It defines its own query language and an algebra you can use to define arbitrary queries to run over the database of your code. And it also defines a set of predefined analyses that are kind of like common, one of them being undefined functions, something we'd like to use. But in the base and how it's implemented is this very generic query system about facts of your code. Right. And here are two examples that I found. One of them is from, the first one is from an article that talks about a way of how you can use Xref to analyze dependencies between your applications in a multi-application project. So this can be very useful, for example, to check that there are no calls between libraries or applications that should never interact between each other. Right. And the second example is from the user docs for the Xref application. And this is the wonderful query that asks for the restriction of external calls except the unresolved calls to functions that are externally used but neither exported nor built in. As you can see, as I said, this is very generic, and you can ask, and very powerful, and you can ask all sorts of advanced and in-depth questions about your code. However, this is not really what we're looking for, right? We're looking for something very simple that answers a single question. And while this can answer this single question, all this abstraction and power that it offers to us comes at a cost, and this cost being performance. So as I said, we can use Xref to find the undefined functions, what we're looking for, and some other use cases that I found really nice articles describing. For example, finding cross-application calls, or removing, finding dead code and discovering that. Unfortunately, this is not the only complexity. because I mentioned releases. And releases are basically a way to package a subset of your code base for deployment of a particular service or a particular system. Right? So let's imagine like a single a project with how many applications do we have in here? Right, we have 6 applications. Right, we have the Acme lib application, which is some sort of generic utility. We have we have 3 services or systems defined. We have the users, the pay system, and the front end system, right? And then for the user system and the pay system, we have some client applications that allow those systems to be called from other releases, right? And so we build 3 releases with our code, from our code base. Each of them includes a subset of our applications. And in order to be sure that no functions exist at runtime that are not included in each of the releases, right? So that to guarantee that no code in our releases will crash with the undef exception, we need to analyze all of the releases separately. And fortunately for us, Xref can do this, but what we need to do first is to actually build the releases. And this might be simple if you have 3 releases and 6 applications, but this becomes problematic if we have a large code base with thousands of modules, hundreds of applications, and several dozen releases, where assembling the releases themselves takes 20 minutes, and running the Xref analysis on that takes another 10. Right? This means that our time to signal is about 30 minutes, which means that this is something that perhaps we can run on CI, and still this would be a fairly slow CI, but it's definitely something that we cannot run after every compilation, right? Or to report feedback to the user inside of the IDE. So we want something better. So let's talk what this better could be. And in particular, one thing that we can almost immediately improve with the way Xref handles things is that when we're analyzing multiple releases in Xref way of working, each of those analyses is completely separate from another. But most of the releases will contain overlapping modules, right? And in many cases, we will have exactly the same information and exactly the same modules that we'll be analyzing over and over and over again with exactly the same results. This is just wasteful, right? So what we would like to do ideally is analyze each module only once. Additionally, we don't want to actually build the releases because this is slow. So what we can do is to analyze the app files without building the releases, and, for example, parsing the information in the rebar config file or the relax config to understand what releases we're going to build from applications, and use this for our base for our analysis rather than actually compiling the releases. Okay, so this seems fine on a kind of high level, but how do we actually analyze the code? And so the first approach and the first idea would be to just start from the source. But this means we need to do fairly involved steps, right? So we first need to figure out how to parse the module in the first place. Then we need to handle include files. We need to handle macros. We potentially need to handle parse transforms that are a significant problem. And finally, to understand applications, we don't really have the app files yet. What we have is the source files that will generate the app files, which potentially adds another layer of complexity that we need to care about. But all of the things I mentioned The compiler already does them, right? Either the compiler or rebar, they already do this. So could we leverage what the compiler does and basically take over with our analysis where the compiler finished, rather than starting completely from scratch? And this is where we enter the Beam files. So Beam files are basically the result of compiling Erlang and Elixir code. For every module that you compile, you will end up with a single Beam file. And this Beam file is a self-contained information about the module. On low level, Beam files are just like a container format. This means they are more or less consist of a set of chunks or a set of sections and some sort of table of contents for the file to be accessed. And some of those sections are required for the code to be executed by the runtime system, but others are mostly, there are some that are helpful for debugging, and some that are like metadata about the module that we could leverage in our analysis. In particular, some of those chunks, some of those more standard chunks are listed here. In particular, some interesting elements would be the code chunk that actually lists actually contains the bytecode, the output from the compiler. We have several tables with information about the source code and with that represent an efficient way for the compiled code to refer to various information about the code. For example, the lockt chunk contains an index of all the local functions in the module. So rather than in the compiled bytecode, rather than saying, please call the function foo, you can say, please call the local function 3, right? Which is much more compact if you refer to this function more than once. Similarly, the export table lists all the public functions of a module. The import table lists not all the imported functions, as you might imagine, but lists all the functions, all the external functions, or all the remote functions that are called from the module. And some others are the debug chunk, the debug info, dbgi, which is an optional chunk that includes the AST for the module, among other things, and the AST being the output of the parsing. And so here we see something that we could actually use for our analysis, right? Rather than parsing the module and getting some sort of symbolized information about the code, we could read exactly the same information from the dbgi chunk. Sorry. So let's look like how our naive approach, or our first idea of an approach to performing this analysis, could look like. We take the Beam file. From that, we read the debug info, realize the AST, or how Erlang calls them, abstract forms. Additionally, we read the information about the topology of releases and about the relationships between applications from the app files and from rebar config. And we use all of that to traverse all of the code and perform the analysis, to build the errors, and to finally report them to the user. And this seems perfectly fine. However, there are some caveats. One of them is that the debug info can be huge. Right? If you have a big module, it can be easily hundreds of kilobytes for a single module. And this is just a lot of data to load, to deserialize, and as well, it's very flexible in what it can contain, and encoded in a fairly complex format, which is the termed binary, what you can call from Erlang. And we ideally would like something that would be simpler to deserialize and most importantly, faster to deserialize. There's a secondary problem with debug info, is that I think since OTP 20 or 21, it might require runtime code execution to figure it out. This is was very introduced for Elixir specifically and is very useful there, but it's problematic if you want to access this data from outside of the beam. And as I said, we need to traverse and analyze the entire code, and this might mean traversing large data structures that we get from debug info, which again is slow. So can we do better? So do you remember when I talked about the various parts of the beam file, I mentioned two tables, particularly the import table and the export table. The export table lists all the public functions in the module, and the export table lists all the remote functions that our module calls. And this seems like exactly what we need to perform our analysis, right? To discover whether all the remote functions in the module are exported from some other module and exists in our codebase Additionally, those tables have a very simple encoding that we can read very efficiently. Right? So for the import table, just have a 32-bit integer with the number of entries. And then for each entry, we have a 32-bit index into the atom table that represents the name of the function, and then the arity, which is another 32-bit integer. And similar for the import table, except we also have the module name in there. But you might ask, okay, so we can discover that a function that we're calling from this module does not exist. But it's not very helpful to tell to the user, well, see, the function x does not exist, and you call it somewhere in here. Right? Ideally, we would like to be much more precise and tell the user exactly where the problem is. And here we come to the big idea of a lot of static analysis tools, or a lot of developer tooling, or like modern developer tooling, is that we can separate two parts of the problem. We can separate finding errors from reporting errors. And the insight is that most of the time, there won't be any errors, right? And if we can make finding errors fast, this means we can report to the user that there were no errors fast, right? On the other hand, if we need to report errors and present them nicely, it's fine for us to spend more time resolving some things and getting some extra information, perhaps even doing redundant analysis, just to make this common case of no errors fast. And so with this idea, we arrive at our kind of final way of implementing our analysis, right? So we take the beam files, and from them we load the import table and the export table that we later combine with the information from the app files to perform our analysis. And then for the files where we detected errors, and only for them, we once again go back to the beam file, load debug info, and traverse it to find the line location or the precise position where the missing function or the problematic function was called, and we finally use that to report errors to the user. And this way, the common, and as I said, with this approach, the common workflow of user just running it and us not detecting any errors is very, very efficient. Or if we detect one error or two errors in the module that the user is actively working on, we only need to load the expensive information for this single particular module, and not for the thousands of modules that might exist in our code base. So let's talk a little bit about why I chose Rust to do this. And I will very clearly admit that one of the reasons for me to choose Rust for this was that I just was interested in exploring Rust and how I could use it and learning it a bit more. And this seems like a great small project to do that. But in doing this, I discovered several very important parts of why doing this in Rust was a good idea. In particular, it gives us very efficient data structures like hash maps, hash sets, graphs, and string internars that are all used within this project. Right. So, for example, we store the export tape, like mapping between module names and then the information about the modules in a hash map, or we store all the relationships between different applications and dependencies in a graph. And finally, for the atoms that we discover, so like function names and module names, rather than storing strings everywhere, which is fairly takes a lot of memory and can be fairly intense. We use a method called string interning that Erlang actually uses for atoms inside of the runtime system. But this means you have one huge table somewhere saying, okay, the atom 3 is the atom called foo, right? And rather than using the name foo everywhere, you can just use the integer 3 instead, which makes it very, very fast to compare the strings and compare the atoms. And what our entire program does is basically a fancy way of comparing strings. But the second interesting part of Rust that I was very satisfied with was the Rayon project, which allows you to trivially introduce parallelism into your program. Right? So in this snippet, we have kind of two implementations. We have both if we remove the parts that are crossed out, we have a single-threaded execution. Right? And so just by adding the part, instead of using iter, using pariter, adding the extra pariter in here and using pariter in here, we suddenly perform all this computation, and this is the main loop that does the analysis in the program. We do it in parallel. And this is extremely, extremely powerful and useful, can be used in a lot of situations. The same parallelization on the part that loads the data is a fair bit more complex, because there we use mutable data structures, because we need to actually collect the information. We don't just consume it. But still, this was a very good experience. And even with Erlang, where doing things in concurrently is fairly easy with spawning new processes, this is even easier. And I was very pleasantly surprised. Yeah, very pleasantly surprised by how easy and then useful it was. And as I mentioned, using Rust, what's beneficial in the structure of the program is that we separated loading of our data from actually analyzing it. Right? This means that when we're loading the data, we can you still hear me? I think I might be having some problems. Hello? So yes, as I was saying, another useful part of doing things in Rust is that we're able to separate the phase where we load the data into our application from the phase where we analyze it. And while in the loading phase, we need more complex data structures, and we need potentially some locks and mutexes to handle with concurrent access to data structures. As you saw in the analysis phase, because we don't mutate anything, we just can very efficiently access the data that we have, and we can remove all of this overhead of those locks and mutexes and things like that, which seemed very, very nice. And finally, there's quite a few existing libraries for handling Erlang code and Beam files that I was able to leverage in here. A lot of them come from the Lumen project, which is the re-implementation of the Beam, so the Erlang VM targeting WebAssembly, and which is implemented in Rust. And it's very interesting to see all of the tools that they're building for Erlang in the Rust ecosystem. Okay, so I'll talked for a while about what are we doing and how we're doing it. So what were the results? So remember that before, using the original Erlang Xref, it took us 30 minutes to get the signal. So with the approach that I've described, it takes us around 200 milliseconds to get the signal on the same code base, right? And this means we can use this tool in completely different areas that we've used them before. And also for comparison, a bit cheaply, I added the time to just launch the Erlang shell, which takes about 300 milliseconds, right? So whatever we wanted to do to build this analysis in Erlang, it would be slower just because of the overhead of starting Erlang itself, right? And so in the time it takes Erlang to start the system, we were already finished with our analysis. And this comes to this interesting idea in developer experience, where you can see we have this kind of phases where the code lives and how people use the code, right? So you first use the IDE to write your code, then you run the compiler to actually compile it and can get some feedback there. Then you can run your tests and again get some more feedback. Finally, you can run more tests on some more checks using CI. Finally, you can deploy a canary of your code, so deploy your change to a subset of nodes in your system. And finally, you deploy everything to production, right? And so with this kind of Xref marathon, what we're trying to do is basically move the signal that the developer gets to the left, or move it so that it arrives to the developer early, right? So even with introducing the Erlang-style Xref, it means we were able to move the signal from production or canary way earlier to the CI or the testing phase, right? And at the same time, thanks to the faster analysis that we can perform, we move the signal from the CI to the compilation phase. Because if it takes 200 milliseconds, we can run this as a post hook on the regular rebar compile call, right? And ideally, we would like to move the signal inside of the IDE, right? Because this is where the developer has all of the context and understands what they're doing, right? So if we show right after the developer writes the name of the function that the function does not exist, they're able to fix it immediately, right? If they get this information like 3 hours later from a CI system, or even from a production node crashing, that they have to go through many more steps to perhaps refresh their memory, what they were doing, where this code lives, analyze the logs, why things are crashing, why things are not going as they should be going. And so it takes much more time to fix the issue, and it's much more frustrating experience for the developer. So this tool is a prototype for now. I don't think it's ready to be used in production code yet. And there are still some improvements to be done. And one of the improvements is that we can make it even faster. So as it is right now, out of those 200 milliseconds, 90% of the time is spent just loading the Beam files. And so the analysis itself takes about 10 milliseconds, right? And out of those 90% of loading Beam files, 20% is spent allocating strings for atoms that we actually don't use because of the string interning. So we can, and then this is mostly because I use the existing library in Rust for decoding Beam files, but we can probably implement something way more efficient for this particular use case, decoding only those two specific chunks for the import table and export table that are fairly small, and skipping all the other information in the Beam files, right? If we wanted, we could also go for lazily loading the Beam files rather than loading everything up front for the analysis and then running the analysis. We could only be loading the files that we need to analyze. And so from our application or our project, we need to analyze everything, but we don't need to analyze everything from OTP and load all the modules from OTP. So we potentially can skip loading a lot of stuff just by doing this. And actually, we can skip analyzing modules from OTP. So this number, 200 milliseconds, it includes analyzing the modules from the project, but it also includes analyzing all of the modules from OTP itself and all of the applications there. So we can restrict the analysis to only analyze what we're interested in, because we probably won't be fixing OTP anytime soon, right? It has its own tests and probably works just fine. And finally, we can look into using even more optimized data structures in Rust. So for example, most of the time when you have the kind of list of functions you import from a remote module, or you call from a remote module, you will have like 1 or 2, maybe 3 functions, right? But as with the current implementation, we allocate an entire vector for each of them. And again, allocations are fairly expensive. And with Rust, we get this much more fine-grained control over the data structures that we can use. And we could use something like the small vec crate to remove those allocations in most cases. And finally, there are some additional features that we're missing from the current implementation, and some places where I cheated, like using a regex to read the app files rather than actually parsing them. And this works fine in app files that are emitted by rebar, but will probably fail horribly in files that are written by hand. It also does not have reading the precise release topology from rebar config. And finally, there's the ignore Xref attribute that rebar's integration with Xref supports, that we probably would also like to support, because there are valid cases where you have those dangling references, for example, just in code that you run in tests or something like that, that they don't cause issues in production. So yeah, I think we're arriving on some conclusions. So I think one of the main points I would like for you to take away is that efficient developer tooling allows for new use cases. and allows for completely new ways of applying them. And that remember this useful technique, that it's not only useful in developer tooling, but potentially in a lot of other cases of separating the detection of errors that has to be very fast from reporting errors that can be much, much slower. And finally, Erlang's late binding or Erlang's hot loading is both a blessing in case you need it, or you can log into the shell and do whatever on the node and debug things. But it's also a curse in cases like this where you have to additionally handle it. And so, yeah, this was my presentation on the Xref.rs project. You can find it on my GitHub. It's still a work in progress, but I hope for it to be useful and production ready at some point. And I'll be happy to answer any questions that might appear now.
Hey, Michal, thanks for the talk. It was very interesting, I thought. We have a few questions still trickling in, but I'll ask the first one that's here. That's when is a stable version planned?
This is a great question, and my answer would be whenever I feel motivated enough to finish it.
Is the goal? Sorry, I was just going to add to that question. If the goal of this is to eventually add to mixed releases, or
so Elixir actually does a lot of this already inside of the Elixir compiler. So Elixir, in the several last releases, there was a lot of work around those particular issues. So first, just around modules themselves. So like, and last releases, I mean like last 2-3 years, I think. So the Elixir compiler does most of those checks and detects those cases. So you don't need to run a separate tool. So this is mostly an Erlang issue.
Yeah.
Yeah.
So we have a semi-question from José Valim. He says, why not use in production now? The worst that can happen is to have a false positive.
Yeah, this is exactly the worst that can happen. Is that right now, because it does not implement the ignore thing, it generates a fair bit of false positives on the code bases that do use this attribute. So yeah, adding handling of that is required, but shouldn't be a big effort. It's mostly deciding on doing it and spending some time actually doing that. Yeah.
Got it. I have one other question for you, more generic one, which is the last talk, we're hearing about Rust and Elixir, and now Rust and Erlang. And my question is, why do you think there's so much overlap there in the communities? Because I feel that's the case. Is there anything special about Rust that complements well Elixir and Erlang?
Yeah, so I think it comes perhaps from two areas. So one would be a lot of people who are interested in Erlang and Elixir are just language enthusiasts, right? So when a new language like Rust comes along, they will be also interested in it. So kind of in a natural way, there will be some overlap between the communities. And finally, I do think there's a lot of potential good cases for collaboration between the languages, or rather for using the two languages together, right? With Erlang doing high-level things and high-level or doing allowing being used for implementing like application logic and things like that, and then Rust being used for those pieces that has to be crazy efficient and crazy performant, while also guaranteeing some form of safety in a like much better safety than C code can. be guaranteed. And I see it used I've seen production use cases in exactly this area, right, where Rust is used as a complement for those places where like this maximum performance is required.
Got it. Okay, we have one follow-up question from Jose. He says, there is no tool in Rust to parse .config files. He assumes Lumen should be able to do it at this point, but maybe that's too large of a dependency.
Yeah, so Lumen does include a parser for Erlang, and I assume we would be able to leverage this parser for computing them. And this is actually my plan, what I want to do in here to leverage the parser that they have. So config files, so the way Erlang actually parses the files like .config that contain terms is that it adds like a small fake function definition in front of the file and a dot at the end, and then tries to parse the file. So we can probably do something very similar with the Rust parser.
Got it. One last question that we just got, and we're going to end it there. But how long until we get an integration with IDEs? Is that in the plans? Yeah,
potentially. So one problem here is that we need to compile in order to get the signal, because we use we get the information from the compiled modules. So this might be a problem in cases you're like the IDE integration is not compiling things on the fly. Like I know like Erlang LS in Erlang does not do that right now. Yeah, and Erlang LS includes some form of the Xref analysis. It's just like a global analysis, so it doesn't do this per application, per release reasoning, right? So it will only tell you if you wrote down the name of a function that does not exist anywhere in the code base. It will report an error to you. It's still better than nothing, and it's still great to have this signal in the IDE that detects more of naive typos and things like that. And so probably those two systems could coexist together, or perhaps we could look into integrating it into the editor integration.
Okay. Okay, that's all in terms of questions. So I see there the link to GitHub. Is there any other way for people to keep track of these, or what you're doing?
Probably this, or the link to GitHub, or my Twitter that I had somewhere on in the beginning that people could explore. That's a lot of slides to skip through. In here, right? So I'm like at Michal Muskala almost everywhere. So, yeah.
Okay. Thanks again for the talk, and talk to you later.
Yeah, thank you.